Okay, thank you. Yeah, thanks for having me in this online seminar. We just talked about that I really find these online activities a good thing, and I hope that some of them will continue if this pandemic is over, because it does give some nice opportunities to sort of be there and meet you, even though I didn't have to travel, which can also be good in the middle of term. So thanks for having me. And yes, the title of the talk is Counting Bitangents of Plane Quartics, Tropical, Real, and Arithmetic. And I'm reporting on some joint work with Angie Cueto and some work in progress with Sam Payne and Kristin Shaw. And there's also some earlier joint work with Yoav Len, which will also be mentioned during the talk. So plenty of people working on tropical bitangents these days. Let me start by giving a rough overview of tropical geometry and tropicalization. Oh, I also realized just now I can't really draw on this, right? I'm so used to Zoom that I haven't paid attention to this. I was going to give some comments using my mouse, but that doesn't seem to work. I'm sorry. I hope we'll manage just talking nevertheless. Okay, so first...
We do see your mouse cursor, though.
You see the mouse cursor?
Mm-hmm.
Okay, good. Yeah, we'll see how it goes. Okay, first of all, as a very rough overview, what does tropicalization do? Tropicalization, you can view it as some sort of degeneration process that takes an algebraic variety and associates some polyhedral complex to that. And the cool thing is that, so it is quite a strong degeneration, but nevertheless, the polyhedral complex that you obtain still has a lot of information about the algebraic variety. And so the big idea is somehow that now with this new tool, you have a way to use methods from convex geometry to obtain insights in algebraic geometry, or maybe the other way around. And in any case, there's this beautiful connection now relating algebraic varieties to polyhedral complexes. Since I want to talk about curves, let's be a bit more special. Algebraic curves are going to be one-dimensional polyhedral complexes, so just graphs. In fact, if we talk about plane curves, we'll just have piecewise linear graphs in the plane, in an R2. Okay. And what does this degeneration really do? So we're using a special field, or in general, a field with a non-Archimedean valuation. You can, for today, just think about the field of Puiseux series over some field little k with characteristic not equal to 2. So what's a Puiseux series? It's just like a power series, only that the exponents that I allow can also be rational numbers. And then for one Puiseux series, I need those rational numbers, which are the exponents, to have a common denominator in order for the multiplication to be well defined, but that's sort of a technical detail. Very roughly, just think of series whose exponents are rational numbers, are allowed to be rational numbers. And then the valuation from this field of Puiseux series sends such a series to the smallest exponent, and that is called the valuation then. And so it sends a series to a rational number, which is the smallest exponent appearing. And now what we do to define tropicalization is to apply the valuation map coordinate-wise. Or as I wrote it here, I'm actually applying minus the valuation map coordinate-wise. That's also only some technical detail, because you can drop the minus, you can not use it, and that will only somehow flip all the pictures of tropical curves that you will be drawing. And it flips somehow from in the tropical semi-field using min convention to using max convention, which are both conventions that are very much used, and in fact you need them both. So since I'm used to it, I chose to have that minus sign here also. But you can just think of tropicalization as applying a valuation map coordinate-wise. And then I think if you think of this, look at some algebraic curve over the Puiseux series, and now we are applying valuation coordinate-wise. we're really forgetting so much. And the fact that we're getting something interesting, and even more, something that still remembers some of the properties of the algebraic variety, I find really very surprising. And so that's one of the first magical results of tropical geometry, so to say. So I wanted to show you one example where I was intending to draw. Now I can't do this, I'm sorry. Let's see how far we get just speaking. I hope it works. I try to speak slowly, and maybe you can give me some feedback whether it works. Let's just think of a line in the plane, yeah? So a line in the plane, which could be given by an equation of the form, let's say, x plus y plus t, where t is this parameter of the previous series, okay? So x comes with coefficient 1, y comes with coefficient 1. 1 are, of course, also previous series, a very simple previous series, which stops and doesn't have any t, but that's fine. And then t, which is also a very simple previous series because it ends, right? T is the constant coefficient. Now, what is easy about lines is that we can parameterize them. So every point satisfying an equation of the form x plus y plus t, I can parameterize by using x and minus x minus t, yeah? And now let's study the different cases that I can have for the valuations of x and minus x minus t. Now imagine for a moment that x is a previous series which has some big valuation, you know, maybe bigger than 1 in any case, yeah, maybe 5/2 or 10 or 23 or whatever, right? Then, you know, sending this vector with coordinates x and minus x minus t to its valuation. For the first component, I will just have whatever the valuation of x is. But for the second, the smallest exponent is now going to be the t that I added, right? I said minus x minus t, and x starts with t to the 5/2 or t to the 23 or something. So now the smallest is at t, right? So I'm going to send such a point to the valuation of x, or minus the valuation of x, and minus 1, right? So that ends up giving me a ray, a horizontal ray with y coordinate equal to minus 1, right? Okay. Now, what if the valuation of x is smaller than 1? Okay. Then if I add the minus t in the second component, I don't change the smallest exponent. Yeah, I'm not changing that summand, and the smallest exponent will still be the same, right? So that means that I'm now getting a ray which is a diagonal ray because it will have the same valuation, and it will be a diagonal ray pointing upwards, starting at the same point as the ray from before. And the final case is what happens if x starts with minus t. Then when I do minus x minus t, I'm having a minus t minus t, which is a plus t minus t, and that's canceling. Yeah. So the lowest term of x, if that starts in such a way that adding minus t just cancels it away, then the second component can have any valuation which is bigger, right? So I'm getting a ray which is of the form minus 1, something smaller. So that's a downwards ray starting at 1, 1. So now let's actually jump ahead. What I described now is essentially something that looks like this green picture here. If you imagine that the center of the point is minus 1, minus 1, yeah? We talked about 3 rays, one pointing to the left, one pointing diagonally upwards, and one pointing down. And we've convinced ourselves now that such a picture like this green picture is actually the tropicalization of a line. And I hope that you can also see that if I change my equation, if I use rather than x plus y plus t, maybe something like x plus y plus t squared also, or maybe tx plus y plus t or something, then what will happen is only that I will shift this point. Yeah, so I will move this picture consisting of 3 rays around, and I will shift it around in the plane, but this form with the 3 rays will always stay the same. So the tropicalization of a line in the plane will always look like 3 rays meeting at a vertex like this. Okay, now let's look at a more complicated example. I wrote here in a polynomial of degree 4 defining a quartic in the plane, right? If I want to view it in the projective plane, of course, I could homogenize that polynomial, but that doesn't play a big role. Let's just use this polynomial for the moment. And all the coefficients are used, very boring Puiseux series because they are very finite. They just have one term, but nevertheless, they are legal Puiseux series. And I can go and tropicalize such a curve, okay? Apply -val coordinate-wise to the 0 set of that polynomial. Of course, now I can't simply parameterize in the way that I've done it for the line, and trying to honestly compute that would be a terrible task if there weren't some additional tools that those of you who heard about tropical geometry before are probably very well familiar with, and others maybe not. I don't want to introduce these basic tools. I want to sort of leave them as some black box in the talk. Everyone who doesn't know about dual Newton subdivisions and the tropical plane curves dual to them, I would like to ask you to please just ignore whenever I say something like involving the word dual Newton subdivisions. I believe that the talk makes sense nevertheless, even without that tool. But for those of you who know the tool, I want you to have that perspective also. So I will mention dual Newton subdivisions every now and then. And yeah, so if you never heard this word before, please just ignore it. And please just believe me for the moment that there is a way to actually compute this degeneration, this -val component-wise, to the 0 set of this curve, and that the picture that you get looks like this. So as I promised, it's a piecewise linear graph in the plane. And let's already observe some features. I promised features of the algebraic curve are going to be visible in this degeneration, even though it is a terrible degeneration. What we can see is, I should also explain that picture, these edges here, these ones, they are supposed to go on forever. These are the ends of the tropical curve. I just can't draw this, of course, yeah, but they never stop. They just continue, like the rays of this tropical line, yeah. They also just continue forever. And we saw before a line had one such ray in each direction. And this is a curve of degree 4 now, and it has 4 such rays in each direction. And this is actually how we can read off the degree, the number of rays in each of the 3 special directions that we're having. Some other observation we can make is that the first Betti number of this graph is 3. So I'm just saying the graph has 3 independent cycles. And that shows that the genus of the algebraic curve was 3, because it was actually a smooth quartic. So it has genus 3, and then when we tropicalize it, we can see this, in this case at least, in the cycles. Yeah. So just looking at this picture, you can see, or you get an idea, even if you don't have much of a background in tropical geometry, I hope you get an idea that what I promised works. You're getting something combinatorial or some convex geometry object, in this case just a piecewise linear graph when you tropicalize. And this graph is still showing interesting properties of the original curve. In this case, for example, the genus and the degree is something we can read off immediately from this tropicalized picture. Okay, let's speak shortly about the dual of a tropical of the plane, yeah. And I think you're all familiar with the dual of the projective plane, yeah, consisting of lines in the original plane. And since we're going to speak about tangent lines to curves, bitangents in particular, in a bit, speaking about the dual plane is very useful, of course. And in the tropical world, it's actually true that it's very nice to think of the tropical line that has its center point at x and y by using again the minus sign and sending this line with the center to just the point minus x minus y, and identifying the dual of the tropical plane like this with an R2 again. Why is it nice to use this minus sign? Because then, for example, incidence relations are respected. Let's look at this picture. So this red line here, that in the dual plane should correspond to a point. Now this point, the vertex of this line could be at something like, let's say maybe 3, 2, right? And then the corresponding point in the dual tropical plane would be -3, -2, which is this red point here. And this blue line here, this maybe has coordinates, what could it be? 1, 3, let's say, right? About 1, 3. The center has these coordinates here, right? And so it corresponds in the dual plane to the point with coordinates -1, -3, which is this blue point here. Okay, and now those two lines meet in one point. This one point in here has a coordinate 1, 2. And vice versa, in the dual plane, we have the red point and the blue point, and there's a line passing through those 2 points, and the line has its center at -1, -2. Yeah, so we see that the incidence relations are nicely respected. If I take the dual of an intersection of two lines, then this is as good as taking the line connecting the dual of one line and the dual of the other line. Yeah. And this is the minus sign has to be used here to make this work. So you have to use the minus sign somewhere in the tropical world, right? But I have to. So this is very common. And if you read something about dual planes in the tropical literature, then you are very familiar with this minus sign. But in the pictures that I'm going to draw in a bit, I'm going to avoid it. I will just send a line centered at xy to the point xy. And the reason for that is that I think the pictures are easier to understand. But this is one thing to keep in mind somehow. So as I said, I'm using the max convention, and the min convention would just be a reflection of the picture. So you might have seen pictures like that one reflected at the point, right? With the 3 rays being in direction this, this, and this. I hope you can see this now with the mouse, right? That's if you're not using minus val coordinate wise, but val coordinate wise, we say it's the min convention. And if I'm doing this now here, I'm actually switching conventions. I'm going from max to min convention in the middle of the situation somehow, but that's okay, yeah, just to keep track of the convention somehow. Okay, now let's start actually bitangent lines. So you might have heard that a plane quartic has 28 bitangents. This is actually a very old theorem already going back to Pluecker. It has been known for quite a long time at this point. But what people found out in the tropical world is that a tropical plane quartic may have infinitely many bitangents, not just 28. But then we go and identify 2 tropical bitangents if we can continuously move one to the other while maintaining the bitangency. What do I mean by this? First of all, what is a tropical bitangent actually? Well, it's a line, of course, and it's a line that meets the tropical quartic in 2 points of intersection multiplicity 2. Okay, now for this picture, you see already that the thing with a meeting in 2 points shouldn't be taken too literally, because here the line is meeting the quartic in a whole segment and not just in a point. But what we do here in such a situation is that we use the so-called stable intersection in the tropical world. And the stable intersection is supposed to be explained with these pictures here. So we are sort of moving our line a little bit away in some other directions. Then we only intersect in 2 points. We compute the intersection multiplicity of those 2 points, and then we take the line back, and then the stable intersection are those 2 points with the intersection multiplicity. And how do we compute the intersection multiplicity? We take, let me explain this with this intersection here. we take the direction vectors of the two edges that are intersecting. So for example, this ray here has direction vector 1, 0. And this edge here, if you really make this computation of how the tropicalization works, you will find out that this direction vector is -1, 2. And then you take those two vectors, put them in a matrix, and take the absolute value of the determinant. And so this is going to be 2 for us here. And so this is actually a tangency point. It's an intersection point of multiplicity 2. And this is not an intersection point, but it's a segment of intersection. And if we now make this determinant computation for these 2 points, down here we obtain as a matrix just the unit matrix 1, 0, and 0, 1 for the 2 direction vectors. So we get a 1. And here we have 1, 1, and 0, 1. So also we get a 1. And so we have 2 points of intersection multiplicity 2 as a stable intersection together. That means the segment has intersection multiplicity 2. So that's also a tangency point. Okay, so this red line that I've drawn here is a tropical bitangent. And now in this picture, you can see already why we can have infinitely many bitangents. Because what we can do now is take the vertex of this line and move it slightly up or down. And if I do this, yeah, these red arrows are supposed to depict this, right? If I do this, then I'm not changing anything about my tangency points. They still look the same. They just happen, this tangency point just happens a little bit lower or a little bit upwards, right? But nevertheless, I will have a tangency point on this edge here and this tangency on the segment. So I will have a bitangent, no matter what, if I just move this vertex a little up or a little down, right? When does this movement stop somehow? It moves as soon as I have the vertex, let's say, about here. I think you can see my mouse, so I hope that helps. And then the ray meets precisely that vertex where this edge ends, right? If I then continue to move upwards, then rather than having 1 point of intersection multiplicity 2, I would have 2 points of intersection multiplicity 1. So I'm not bitangent anymore, right? And the same as I move downwards, I can move until roughly about here. And then my ray meets this vertex here, and then I can't move any further down. And what you saw in this example now is an example of a tropical bitangent class. So we used this equivalence relation, saying that tropical bitangents, of which there may be infinitely many, are equivalent if I can move them continuously, like here, without losing the bitangency. And then I take such an equivalence class. And in my case, this equivalence class consists of such a segment starting here and going up here. And every point in this segment stands for the vertex of a line which is a bitangent. That's shown in this example. This is precisely the tropical bitangent class. As I said, using the identification of the dual tropical plane without the minus sign. So I'm just identifying a point, like for example, this point here with the tropical line that does this. So it has this horizontal ray meeting the vertex here, and it has this vertical ray meeting the edge down there, and it has this diagonal ray, right? And a point somewhere in the interior of this edge would correspond to a tropical line like the one we just saw on the slide before. Oopsie, like this one here, right? This would be an interior point in this segment here. Okay, so this is an example of such a tropical bitangent class. Okay, now let's continue with this example. Actually, I should say something about the Newton subdivisions here. You see all those pictures next to my tropical quartic. These pictures are for those of you who are familiar with dual Newton subdivisions. So you will recognize them and you will see, aha, this is really dual to the quartic. And on this slide here, you see that in these dual Newton subdivisions, I've drawn some parts in color and then highlighted them again. And these are sort of the parts of the dual subdivision which are dual to the features of my tropical quartic that are in charge of the tangency, of the intersections. Okay, this only as a side comment to those of you who are familiar with dual Newton subdivisions. Everyone else, just forget it. And focus on this tropical bitangent class, which has those two vertices. Okay, now let me present some theorem already, or a case in a big theorem, so to say. If you pick a quartic polynomial over the previous series with complex numbers now as coefficients, yeah? And if I pick such a quartic polynomial such that the tropicalization of the corresponding curve is precisely this tropical quartic, then this algebraic curve B of Q is going to have 28 bitangent lines, right? And I can also go and tropicalize the bitangent lines. And what will happen? Exactly 2 of the 28 bitangent lines are going to be mapped to this point here. Exactly 2 will be equal to the tropical line that does this here. Horizontal ray, vertical ray, diagonal ray. And exactly 2 will be mapped to the lower one, okay? Horizontal ray here, vertical ray here, diagonal ray here. And nobody is going to be mapped to any point in the interior. Yeah, what I'm saying here is that this tropical bitangent class has 4 lifts. When I say lifts, I mean going backwards under tropicalization. Yeah, so finding the bitangents to the algebraic quartic that tropicalize to these lines. Yeah, so it has exactly 4 lifts, and those 4 lifts are divided as follows: 2 go to the upper vertex, 2 to the lower vertex, nobody to the inside. Okay, let's collect a few more facts. We've seen already our plane quartic has 28 bitangents. Our tropical plane quartic may have infinitely many. We use this equivalence relation in the tropical world, saying 2 tropical bitangents are equivalent if we can move one to the other, maintaining bitangency. And then if we do this, Baker-Len, Morrison, Pluecker, and Wren proved that a tropical quartic in R2 has precisely 7 bitangent classes. Okay, and now if we look at this example from before, I gave you one example of a bitangent class, and I told you that this one has precisely 4 lifts. And now just comparing the numbers, you would want to make the guess that every tropical bitangent class has precisely 4 lifts, because then 7 times 4 gives you your 28 and everything works out. And the good news is the world is exactly that nice. So Chan and Girardilok, they proved that if the skeleton of the tropical quartic is a K4, so that's just a certain feature on the graph, yeah, the graph underlying the quartic. If I leave away all the ends, so to say, if this is a K4, then each bitangent class has 4 lifts. And together with Len, I proved that if you take a generic smooth tropical quartic in the plane, then the general statement actually holds. Every bitangent class has precisely 4 lifts, which is nice, I think. Okay, now let's change the situation and let's talk about the real world. Let's talk about quartics over the real numbers. You might have seen some pictures of quartics over the real numbers. Of course, they can have different topology. They can have different numbers of ovals. Yeah, ovals just meaning these, well, not quite circles, but shapes that are formed by a quartic. You can have 4 ovals, or you can have 2 nested ovals. There are different possibilities how a real plane quartic can look like. And this topology has been classified. Oh, I don't even know by whom, but so the task to classify the topology of real plane curves goes back to Hilbert, and then many people contributed, and I don't know who solved the question for quartics. But it's also very old, of course. And it's going back to Pluecker that a real plane quartic can have 4, 8, 16, or 28 real bitangents. And the question, how many, actually just depends on the topology. Yeah, if you have 4 ovals, it's going to be 28 real bitangents. If you have less, it's one of the less numbers. Now, when I learned about these possible numbers for real plane quartics, I have to admit that only looking at the numbers intrigued me somehow, because you see that they are all multiples of 4, right? 4, 8, 16, 28. They're all multiples of 4. And we just learned that over the complex numbers, one of those 7 tropical bitangent classes has 4 lifts. So with UAF already, we were conjecturing that if you change your field and work over the reals, and then consider a tropical bitangent class of a generic smooth tropical quartic, then you have either none or 4 lifts over the real numbers, but not something partial, right? And then knowing this, that would sort of give some explanation of why all these numbers are multiples of 4s, right? Because there's the tropical picture, the tropicalized picture gives you a way of grouping into 4. And then for some of the 7, maybe you have only complex solutions, but for others, you actually have real solutions, but then not all 4 solutions are real, right? Okay. And yeah, this is now actually a theory proved by Angelica Cueto and me. And to prove this, what we did was a complete combinatorial classification of how bitangent shapes can look like. And then we sort of used local lifting computations to argue why this is true, that either all 4 solutions over the complex numbers are already real, or none of the 4 solutions is real, they're only complex. Let's look at one example. In blue, we have a tropical quartic like the one we looked at before, so I hope that you're all happy to believe that this is really the degeneration of a plane quartic in the sense I described earlier, using val or minus val component-wise. In black, these are the 7 tropical bitangent shapes, okay, of this quartic. Okay, let's convince ourselves that this is actually true. So the one labeled 2 here, this is actually the one we looked at earlier, yeah? So this vertex corresponds to this tropical bitangent with the edge intersection here and the intersection on this edge of direction -1, 2, right? And then number 4 is sort of very symmetric. It meets a segment here, and it meets this symmetric edge down there. So I think you're all hopefully all happy to believe that this 4 is a bitangent. Then if we look at 5, 6, and 7, they're all very similar because they have 2 intersections with edges, yeah, that give a multiplicity 2 then, as we saw before, here, for example, or here, like this, right? Okay. 3, we see now for the first time a 2-dimensional bitangent shape. Why is the 2-dimensional thing happening? Think of a point in the interior for the moment and think of the corresponding line. It means the interior of those 2 edges, right? And that means now I can move it upwards and I can move it to the right or left. And I won't change this tangency behavior, right? And for that reason, I'm actually getting a 2-dimensional bitangent class here, which looks like a rectangle in this case here. Now, number 1 is the most complicated one, and it would maybe be too much to go through all the different pictures. What I can tell you about 1 is that there are really many different intersection patterns combined in just one tropical bitangent shape, which I also find interesting. But yeah, it gives you some idea of that these shapes can look sort of way more complicated than just points or edges like the ones that we looked at in more detail. Okay, on the right, this is again only for those of you who are familiar with dual Newton subdivisions. Here I've just highlighted the features of the dual Newton subdivision that are in charge of the tangencies, so to say. This here, for example, are of course the 2 dual edges to those edges, and this is dual to this segment here as we saw before. Okay. Okay, this, I hope it doesn't frighten you, this slide. It does look a bit terrible if you see it for the first time. But this is the combinatorial classification of the tropical bitangent shapes up to symmetry. Okay, so for example, we saw points, we saw edges, and the edge could also be a vertical edge. That's a symmetric case then, right? So it's not listed separately here. And then what else did we see? We saw, yeah, in this case, it's a parallelogram now. The case where it's a rectangle, like in the picture before, will be a symmetric case. And the last picture, we saw something like this here, like the S. Yeah, you see that we're using a lot of numbers and color coding in these pictures here. Let me explain what this color coding means. So if I draw something in black, I mean the bitangent class doesn't meet the curve at all, whereas red lines or vertices mean they meet the curve. The red parts are also part of the curve. And vertices that are white mean they are vertices of my curve. And points that are just red means they are points on edges of the curve. So if we look back at this example, for example, here it's also color-coded already. We've seen those two red edges. This is supposed to be red also. It's probably just hidden behind the blue. Yeah. So these edges here are red, and in white the vertices of the curve. This is how we use the color coding to really give a full combinatorial classification of the bitangent classes. Yeah, and of course I don't have the intention of honestly making you understand why we have those different shapes and how we classify also. It would be way too much. I'm only showing the slide because I'm hoping that you get an impression of this task somehow, an impression of what this combinatorial classification gives you. And of course, I'm hoping you recognize some of those shapes and you feel sort of comfortable with this picture, saying, okay, some of those shapes I've seen and I know, and for the other shapes, let's just believe for the moment that they actually found them and that they completely classified it like this. Okay, and then this slide is only for those who like dual Newton subdivisions. This is then a classification of all the important features in the dual Newton subdivisions corresponding to one of those bitangent classes. This picture is a special case of this type A. We're here also using some color coding. And you know, I think if you're interested in details like this, then it's probably a good idea to use the time after the talk to discuss it. For the moment, let me just say this is a case like A, an example like A, where I'm also explaining the notation of the points that I'm using here. This is something that is actually for everyone. The dual Newton subdivision, if you know that or not, it has something to do with the Newton polygon of your polynomial. And Newton polygon of your polynomial, I suppose you've all seen. We're talking about a quartic polynomial right now. So I'm having monomials from constant to degree 4, right? So this, you can recognize this as the Newton polygon. And these labels here just denote some monomials in my polynomial, so to say. And if you know this, you can also make some sense of this table. Again, it's a terrible slide. I certainly don't want you to digest any details of this slide. I only want to give you an impression. And I want to tell you how to read this table. If you later care for a certain case and really want to go through the details, then you should know what we're doing here somehow. We're giving lifting conditions. That means we're telling you inequalities that have to be satisfied in order for a certain bitangent, tropical bitangent class to have 4 lifts over the real numbers. Yeah, because we learned from the theorem before that each tropical bitangent class over the reals either has 4 real solutions or no real solutions. It has 4 complex lifts, and of those 4 complex lifts, either everyone is already real or no one is already real. Okay, and we're giving you inequalities here that decide in which case you are, whether you lift, whether you have 4 lifts. Yeah, and these inequalities we refer to here. So the Sij are the signs of the coefficients of your quartic polynomial. Yeah, so you have a quartic polynomial, whose tropicalization we are looking at. And in the real case, of course, the coefficients of my polynomial are real numbers, and they have a sign. And so the coefficient in front of the monomial, x to the I, y to the j, has the sign Sij. That's my notation here. Okay, so this is the sign in front of x squared, y squared, and this is the sign in front of y to the I, whatever I is, right? And so you can read this now by just looking at the signs of the coefficients of your real quartic, and then you can answer using this table whether your tropical bitangents lift or not. Okay, let's look at one example. It's the same picture that we looked at before, the blue tropical quartic, tropicalized quartic, and the 7 black or gray tropical bitangent classes. And we played with this example, and we found actually out that if you change the signs of your coefficients, you can reach all the possible numbers of real bitangents. Yeah. So Pluecker already told us that for real quartic, we can have 4, 8, 16, or 28 bitangents. Depending on the topology, which is listed here, yeah, you can have 4 ovals or 3 or 2 non-nested in this case, or 1 oval. Yeah. And so Pluecker told us that these numbers are possible, and what I'm saying here is that we can realize all those numbers already using different lifts of this blue tropical quartic. And when I say different lifts, I mean different real polynomials that give me the same tropicalization, the same tropical quartic. And when I say different real polynomials, what I mean is I play with the signs. Yeah. So for example, in the first case, I can pick only positive signs. And then it will be the bitangent number 1 and number 3 that lift, this guy and this guy. This will have 4 lifts over the reals, and this will have 4 lifts over the reals. And so altogether, I will have 8 real bitangents. And all the others are going to have lifts which are complex but not real. Okay. Now, if I change the sign of the coefficient 3, 1, of the coefficient in front of x cubed y, then suddenly 1, 2, 3, and 7 are going to lift. And each lifts with 4, of course, so I'm going to have 16 real bitangents. And so on. And so you can see that only with this one tropicalized quartic, I can already realize all the numbers that Pluecker told me that they can possibly exist. And yeah, that also raises interesting questions, which will appear on the coming slide. But before we go to more interesting questions, some corollaries of this combinatorial classification that Angie and I have done. One thing is a tropical bitangent class is a tropical convex set, which is something that just falls out of the classification. You look at those pictures that we've drawn, and if you're familiar with tropical convexity, you look at them and you say, aha, they are all tropically convex. Another corollary is if you look at those real lifts of tropical bitangent classes, then it turns out they are already totally real, which means that not only the coefficients of my line are real numbers, but also the points of tangency are real. Yeah, and that's actually also a surprise in a sense, because there exist examples of real quartics that have bitangent lines which are real, but which are not totally real. So their points of tangency are actually complex. So if you draw the real picture, you don't see the point of intersection. You only see an oval and a line that doesn't even meet the oval, yeah, or several ovals and a line that doesn't even meet, but it meets in the complex world, of course, and it has a tangency in the complex world. So examples like that exist, but we don't see them when we tropicalize. Why is that the case? Well, because we're making a restriction in the tropical world. Of course, we're dealing with smooth quartics in the tropical world also. And so that means that all those examples where we have real lines which are not totally real, they must tropicalize to something which is non-smooth. And for those, the techniques are only partially established at this point by Joaf and also some of his collaborators. Okay, now what questions remain if we look at that? Well, this is the first question I sort of already talked about. What are the tropicalizations of real quartics that have real but not totally real bitangents? So they must be something not smooth, but what can we say about them? There's still a lot to be found out, right? Then earlier we talked about how those numbers are related somehow. So we have 7 tropical bitangent classes. We have 4 complex lifts for each, and we have 0 or 4 real lifts for each. But how can we conclude that Pluecker's theorem holds for the also for the tropicalizations, right? How can we conclude that we obtain altogether only 4, 8, 16, or 28, and not maybe something like 12 or 20, right? If I had 3 tropical bitangents that would lift and all the others not, then I would get 12. Why is that not possible? The tools that Angie and I developed do not answer this question. This must be, you must look at this question more globally somehow. We looked at it locally at, one tropical bitangent shape, one by one somehow. But my student, Alheidis Geiger, together with Marta Panitsut, they are working on the global argument, which is necessary somehow. And they just very recently proved, actually, that there are always 4, 8, 16, or 28 relifts. So they're sort of confirming Pluecker's theorem using tropical methods. But from my point of view, this is more than just a confirmation of Pluecker's theorem using tropical methods. This is giving a way to study lifts of tropical bitangents also over other fields and to make statements about bitangents to quartics also over other fields. And I'm quite certain it will be used like that also in the future. Okay. Right. And the last question, which is maybe more interesting for those of you who are familiar with tropical geometry already, you might have seen tropical curves not only in the plane, but also in different models of the tropical planes. And what about bitangents of those? And these are out of reach of the current methods these days. So we don't know anything about such tropical quartics and their bitangents. So there's still a lot to be discussed and a lot to be found out. I want to turn more and speak about real bitangents and introduce the so-called avoidance locus. So this, what you see here, is a picture of a real quartic with 4 ovals, just a sketch, right? And the avoidance locus consists of all real lines in the, in the dual plane again, all real lines that do not meet the curve. For example, this red line that I've drawn here doesn't meet the curve, so it's part of the avoidance locus. And then there's a theorem by Kumar, going back to Vinnikov, maybe some others also, that tells me that every connected component of this avoidance locus has precisely 4 bitangents in its closure. And we can sort of see this in this picture, so we can move this red line around, staying in the avoidance locus, right? But then if we move it such that it meets those 2 ovals, then it's a bitangent, and then we are sort of at the boundary of the avoidance locus, right? Or we could move it like that. You see those 4 blue lines that I've drawn here. These are the 4 bitangents which are in the closure of the connected component of the avoidance locus given by this red line here. I think this picture is very convincing. I hope that you can all see it in a sense for this, sketch, so that you have a reason to believe that this theory holds. Okay. And now, why did I get excited by this? Well, because here's yet again some sort of grouping bitangents into 4, right? Tropical geometry groups bitangents into 4 by mapping them to the same tropical bitangent class. And real geometry groups bitangents into 4 by checking, in which connected component of the avoidance locus they correspond to, right? And of course, I wanted to know whether this grouping into 4 has something to do with each other. And it turns out, and this is something I'm investigating together with Sam Payne and Kristin Shaw, and this is still work in progress, a tropical bitangent class, which is liftable to the reals, is actually the tropicalization of a connected component of the avoidance locus. And that means that the four real lines which are in the closure of this connected component will map to 4 points in this tropical bitangent class, which are liftable. So the tropical grouping into 4 and the real grouping into 4 actually coincides. And this theorem also tells us a bit more about the structure of tropical bitangent classes, right? For example, the fact that they are all convex. Angie and I observed this, but it was just sort of a byproduct of this big combinatorial classification. And we just, the proof was just, hey, look at all those shapes. They are tropically convex. But now we have a bit more of a reason why they are tropically convex, because the components of the avoidance locus are convex. And convexity is preserved under tropicalization, so they had to be convex. So I like this, this way of understanding a bit more of why the tropical bitangent classes look like they look. I have to admit now that since I'm using those big slides, I don't even see the clock anymore. So I don't know what time it is. Can you help me out? Is there still time to talk a bit more about arithmetic counts?
Yeah, I think so. So we have 55, but I think you can take your time. We started a bit late, so.
Okay, good. So then let's just add a bit of an outlook treating arithmetic counts. So my perspective on arithmetic counts is that we're trying to establish a universal theory of counting over any field. I learned about arithmetic counts not so long ago, so I'm clearly not an expert here. It's also not such an old subject. It's developing since maybe let's say about 10 years or so. I can't be that precise. I didn't check the date so carefully. So we want to have a universal theory of counting, but what we're doing is we're not counting geometric objects one by one, but we're sort of counting classes in the Grothendieck-Witt ring. What's the Grothendieck-Witt ring? It contains all formal sums of isomorphism classes of quadratic forms from some vector space to my ground field. Okay, why does that tell us something about different fields? Let's look at an example. If we take the complex numbers, then this matrix, of course, defines a quadratic form from the two-dimensional vector space over C times the two-dimensional vector space to the ground field, because I can multiply a vector from the left and a vector from the right, right? That's the usual linear algebra way of writing down quadratic forms as matrices, right? And then if we're working over the complex numbers, of course, we can just use a base change using this matrix 1, 0, 0, I. And with this, we see that this matrix is actually equivalent to just the unit matrix over C. Yeah. So the class in the Grothendieck-Witt ring would be one and the same. Yeah. But if we tried to look at those two matrices over the real numbers, then of course they are not equivalent, right? Because I is, just not a real number. It's the complex unit, right? So I can't use this matrix to base change, and I also can't use any other matrix. Those two are just not equivalent if we work over the reals. So I hope that this example tells you a little bit that if we're working over C, then an arithmetic count is very similar to just a number, because if we're working over C, then it's just the numbers of ones on the diagonal that matters, because I can make any quadratic form look like a matrix with a certain number of ones on the diagonal. Yeah. So over the complex numbers, using these equivalence classes in the Grothendieck-Witt ring is very close to just adding numbers somehow, to dealing with numbers. Whereas over the reals, we suddenly get other meaningful real invariants. Okay, so what is known in the arithmetic world? As I say, we don't count, but we associate an element in the Grothendieck-Witt ring to a geometric object. And there exist arithmetic counts of lines in cubic surfaces, for example, by Karsten and Wickelgren, plane curves satisfying point conditions by Levin, and bitangents of a quartic by Larsen and Vogt. And this is a rather recent paper from 2019. And yeah, this caught my attention, of course, and I tried to investigate what's happening on the tropical side with those arithmetic counts. So if you're familiar with counts of plane curves satisfying point conditions, you might have heard of Val-Georget invariants, which are certain counts of real plane curves satisfying point conditions. And this is what you get if you insert the field to be R for Levin's arithmetic count of plane curves. Yeah, so you get something else which is meaningful in the real world. And what can be said very generally is that tropical geometry plays some sort of intermediary role. For example, for this case of plane curves satisfying point conditions, because there exist the so-called quantum counts of plane curves which use tropical techniques and which show you how you can somehow interpolate between complex counts and real counts. So it was somehow very intriguing to me, and I thought tropical geometry, which plays an intermediary role for real and complex counts, it has to also play some role for those arithmetic counts. And so Sam, Kristin, and I started working on this. And first what we did, the first step is somehow to generalize the lifting statement by Angie and me to arbitrary fields. And it's actually still true that a tropical bitangent class either has 0 or 4 lifts, no matter which field you're working on. Either everyone exists in your field or no one exists in your field. It's also true that if you don't have lifts in your field, you have to pass to a quadratic extension, and quadratic extensions are all you need. Then all your tropical bitangent classes will lift, which is sort of nice also, I think. It's also true that the real versus totally real analog does not quite hold like this anymore. It holds only for fields in which 2 and 3 are squares. For fields in which 2 and 3 are not squares, there's precisely one tropical bitangent shape that doesn't satisfy this. Also somehow weird and interesting to me. Yeah, and then also, actually, I think by now you can call this a theorem. We're still working on the paper, but we proved it. The element in the Grothendieck-Wittring that belongs to the 4 bitangents in a tropical equivalence class is a Laurent monomial in the coefficients of the quartic, and possibly some roots that you have to add if you have to pass to a quadratic extension to make your bitangents lift. And this is again one of those horrible slides that's only meant for you to get an impression of our current work, of what we're doing right now. So you see, this is sort of an even finer classification of the bitangent classes that we have on the tropical side. And we had to make it finer because symmetry is not preserved. And then you see here 4 elements in the Grothendieck-Wittring. And so it's a computation that we've done, but that we're still trying to somehow make more digestible. So for example, the most recent outcome from just last week was that we could prove that for many of the tropical bitangent classes, the sum of the arithmetic counts is just 2 times the hyperbolic form, or hyperbolic quadratic form, which is also nice, I think. But it's not true for all tropical bitangent classes, only for very many. So yeah, you can see there's still many question marks left. But I hope that you can also see that tropical geometry is a nice and interesting tool that helps you to somehow combine several counting techniques and counting over various fields, in particular counting over the reals, over the complex, or over some other field. That's all has something to do with tropical geometry, which is not so surprising because tropical geometry works over any field. But it's to me, it's combinatorially interesting how we can say very similar things for many fields, and how we sometimes have to pay attention and make particularly requests like 2 to be a square also. So I hope that you also appreciate this fact that tropical geometry tells us so much about different ways of counting. And as I said, this is all work in progress, so I think it will continue, and I hope I will have to say more at some point. And that was all for today.